Chinese Adaptive Computer Acceleration Platform Versal architecture. Abstract. In this paper, we describe Xilinx Versal Adaptive Computer Acceleration Platform, ACAP. The ACAP is a hybrid compute platform that tightly integrated traditional FPGA programmable fabric, software programmable processors, and a software programmable accelerator engine. The ACAP improved over the programmability of a traditional computation platform by introducing newer compute models in the form of the software programmable accelerators and by separating out the data movement architecture from the computer architecture. The Versal architecture includes a host of new capability and including a chip pervasive programmable network on chip, the NOC, and the Imux registers, and a computer shell, and a more advanced SSIT, adaptive SSIT, the adaptive deskew of the global clocks, and the faster configuration, and other new programmable elements, as well as enhancement to the CLB and interconnect. We discuss these architectural deployments and highlight their key motivation and difference in relation to the traditional FPGA architecture. Keywords: ACAP Versal FPGA Stack Silicon SSIT, Adaptable Computer Acceleration Platform, Math Engine, NOC, FPGA Architecture, and FPGA CAD, and Xilinx. Introduction. It's well known that benefit from the process technology scaling and reducing. The benefits of new technology nodes alone are often insufficient to justify the development cost of a next generation device, forcing more aggressive innovations at architecture and system levels. With the recent explosion of the data and surge of the machine learning and AI applications, the needs for compute have also been increasing due to the high cost of sub-16nm technology nodes and the continuously changing requirement of these applications. Developing associates for these markets is challenging by the virtue of their configurable nature. The field programmable gate arrays excel in application with varying workloads and requirements, circumventing the economic challenges of heterogeneous compute platform with configurable hardware. So FPGA platforms have recently been deployed on the cloud to democratize these systems at a large scale. The figure 1 is metal and transistor delays for quad routing the resources across different technology nodes. Normalized to the total delay is 28 nanometer. As many compute-intensive solutions today operate in a thermal envelope and are thus power limited. Although the power and the delay per operation drop with the technology scaling, they no longer drop at a rate that satisfies exponentially increasing the compute demands. So the metal resistance is another critical challenge that worsens with the technology scaling. Although the wire distance is shrink with the lithography, a wire cross-sectional area shrink quadratically and resulting in the next net increase in resistance generation. Hence, even though the transistor delays continue to decrease with the smaller transistors, total path delays may not. In Figure 1, we show the minimum wire pitch delays of an interconnected routing resource over several technology nodes, assuming that the physical existence of a given logical span also scales. Despite the physical distance shrink and transistor delay speed up, total delay actually increases with more advanced process nodes. Hence, we are forced to use thicker metal with a lower resistance to reduce wire delays. As technology scales, metal resources therefore become more extensive and architectural changes need to be made to use them more efficiently. One of the hurdles to greater adoption for traditional FPGA architecture is ease of use. Recently, there has been a drive toward software solutions to improve the user abstraction level to interact with FPGAs. However, widespread use of the reconfigurable hardware without the requirement of the expertise remains elusive. Figure 2 is a Versal representative device floor plan. In this paper, we present a new class of reconfigurable devices called the Adaptive Compute Acceleration Platform (ACAP), invented by the Xilinx to provide a solution for the compute and communication needs of the applications. So we describe the 7nm based Versal architecture, which is a new reconfigurable platform architecture that solves the economic and technological and ease of use challenges mentioned above. We provide a general overview of the architectural changes with some experimental results. So we limit the scope of this paper to reconfigurable fabric and related subsystems. In section 2, we describe the features of the Versal architecture at a high level and distinguish it from a traditional FPGA. And in section 3, we describe the programmable fabric and the various enhancements made to tackle the economic and technological changes. Section 4 describes a fourth generation stack, the silicon interposer technology with new capabilities for multi-die devices. We briefly describe the clocking structure, hardened network on chip, NOC, and the configurable system in section 5. Section 2, floor plan. In figure 2, we show a representative device floor plan for the Versal architecture-based ACAP. The fabric portion of the device is similar to a traditional FPGA, including resources such as LUTs, flip-flops, and DSPs, and VRAMs, and a relatively recently introduced Ultra RAM. All arranged in a columnar topology, the changes to these blocks are described in section 3. What makes ACAP unique is that it hardens all the necessary platform management functions and separates them from the FPGA core logic. The processor and the platform management controller occupy the lower left region of the chip, that is adjacency of the processor subsystems, PS, 2 GB transceivers, GTs, and memory controllers, and the NOC enables those blocks to be used together without any of the fabric being programmed. GT can occupy the left and right edges of the fabric regions, and note the high-speed IOs in the Versal now run along the bottom and optionally top edge of the die. Top edges of the die. Integrated with those IOs are hardened memory controllers to interface with offshoot memory such as DDR and HBM. Across the top of this example Versal architecture-based floor plan is an array of the AI engines designed to accelerate math-intensive functions for applications including the machine learning wires. Finally, the chip-pervasive hardened network on-chip NOC augmented the traditional fabric interconnectivity and enables a new class of high-speed and system-level communication between the various heterogeneous features, including PS, DDR, AI engines, and FPGA fabric. Section 2.1 or 2.1 Hardened features. A key benefit of FPGA is adaptability provided by a configurable fabric and other on-chip compute and memory blocks. One recent trend has been the use of the FPGA for accelerating various functions that were traditionally implemented on CPU. In this environment, most of it prefers a standardized This standard application components like memory controller and PCIe generally don't benefit from the adaptability enough to adjust it justify their cost in soft fabric. So, substantially portion of the FPGA fabric can be spent on this functionality as illustrated in Figure 3, which shows the replacement of the shared logic that performs static platform level functionality when an instance of the AWS F1 FPGA is invoked. Moreover, the design effort is spent in ensuring that these platforms meet timing and do not interfere with the place and route of the actual accelerated cores. This logic implements memory controller, PCIe connectivity, and the provide port for rest of the compute to interface with the memory controller. Additionally, this solution requires loading a minimal state configuration prior to loading any user-specific functionality. In contrast, the memory controllers, PCIe, and associated interfaces are all hardened and directly connectable in the Versal architecture. So as a result, once powered up, the FPGA boots up in a steady state ready for use without a need for a bootstrap any soft logic first. This reserves the FPGA fabric fueled for the user functionality. Figure 3 is a static platform logic for the AWS F1 instance based on the ultra-scale architecture. So the next is, the functionality. And also helps non-traditional FPGA users the productivity use the ACAP without a detailed device knowledge. Some features are ubiquitous enough to include all devices such as hardened memory controllers and NOC infrastructures. However, the other blocks are market specific and are already necessary. Therefore, Versal architecture comprises a frame network that enables swapping different features in and out of the different devices. For example, some devices have AIEs along with their top edge. Other devices have IOs or fabric along with their edge. Similarly, some devices have HBM interfaces in place of DDR/IO and controllers. A to D converters can replace GTs and a variety of smaller hard IP blocks for error correction and MIS blocks, interracking, and PCIe, and etc. can occupy the slots within the fabric library array. In this respect, the Versal architecture enables a platform that continue to trend toward enabling families of domain-specific devices. So section 2.2, perimeter I/O. Since the Vertex 4 Xilinx FPGA have had columnar IOs, there are several advantages to columnar IOs, including the tight integration with the fabric and area efficiency. However, multiple technology trends have led to perimeter IO being more appropriate for the Versal architecture, so the IO cells don't tend to shrink with more Bauer's role. Similarly, as noted, the cost of using long metal wires has increased as a result over the past generation of FPGAs. The increasing interconnect delays and clock skew incurred by metal crossing over a large I/O columns have led to the software tools participating in the design across these boundaries. So additionally, I/O packaging trays break out from the die interfere can challenging and performance limiting. As a result, the implementation of perimeter IOs enables higher performance IOs and less fabric disruption. To the 3, regularity. Overlays have become more powerful and popular among FPGA users. Use of a domain-specific overlay has a substantial productivity benefits. These overlays are very structures designed using analytically techniques to implement them LUTs tools to extract more performance from FPGAs rather than traditional generic RTL-based implementation tools. One way to make overlays easier to implement is to have a very regular patterns of fabric columns. However, in a traditional FPGA architecture, even a perfectly repeated columns of fabric don't enable a perfect stamp and repeat of a user IP. So because communication interfaces to those blocks would not be identical, each repeated IP would need to be uniquely configured to enable routing and connection to the external environment. The Versal architecture based on devices are the first class of the modern devices from the Xilinx that offer a high level of the fabric regularities. The composition of the clock regions repeats at a regular intervals across each device, so this permits two significant productivity improvements. It permits relocatability of IP in both X and Y directions without having to do a complete re-implementation. So moreover, if each IP communicates with the rest of the design over the NOC discussed in the section 5.2, the even global communication interfaces do not have to be re-implemented when an IP is relocated. Thus, Versa enables the possibility of importing the pre-implemented, placed and routed IP and replicating the same IP at different location. Utilizing the regularity also can enable hierarchical place and route run times to be several times faster than a flat implementation flows. 3. Programmable fabric. Compared to the ultra-scale, the Versal architecture has some significant differences to each fabric, that is, the CLB and the interconnect and the DSP and the BRAMs and the URAMs and etc. Various design choices were made to increase device capacity and facilitate more complex design in a technology with metal resistance and cost challenges. We briefly describe the design choices and present some experimental result in this section. The 3.1 CLB. The CLB is a Versal architecture, contains 4 times the number of LUTs and registers, 32 LUTs and 64 registers. At the ultra-scale CLB, 8 LUTs and 16 registers. Sorry again. Okay, the components are noted in Figure 4. In Figure 4, here, this is a Figure 4, like here, register, LUT RAM, and SRL capable LUT, and Imux registers. The internal of the CLB, such as wide function, muxes, carry, chain, and internal connectivity, were redesigned to increase the total device capacity by reducing area per utilized logic function. A dedicated local interconnector structure resides within the CLB to support more versatile intra-CLB connectivity. By enlarging the CLB to include 4 times the number of the logical elements, so we subsume a significant fraction of local nets internally, thereby reducing the global track demand. Each of these enhancements are discussed in detail below. 3.3.1 The Versal-based lookup table. Compared to the ultra-scale, the lookup table LUT in Versal is enhanced to increase effective tacking density and functionality. The ultra-scale 6-bit LUT has 2 outputs, and then it can implement either any 6-input function or 2 independent functions of up to 5 unique inputs. As shown in Figure 5, a 6-bit LUT in Versal has an additional output O5_2 and some circuitry on the second fastest input. This enables us to pack 2 independent functions of up to 6 unique inputs. So our goal of the implementation tools is to maximize the device utilization by packing the logic into fewer logic elements. If 2 LUTs are placed close by, merging them into one physical LUT frees up additional resources while minimally
perturbing in the natural placement of the design. Figure 6a shows a packing density improvement on a design suite of customer designs. So it illustrated the number of the legal LUT merging candidate within a given radius for a Versal, normalized to ultra scale. For example, if you permit merging of the LUTs, separate its displacement in by less than or equal to distance over 5. In Versal, we find 21.5% more candidates to merge than in an ultra scale, thus increasing logic per unit area accordingly. Like this here, the ultra scale 6 LUT and the B is Vers 6 LUTs. This is figure 5, is a 6 LUT comparison between the ultra scale and the Versal. Okay, so now also due to Versal is a dedicated and fast LUT to LUT cascading path, which improves the time for passes between multiple levels of logic. The vertical cascade path days chain adjacent to LUTs together by muxing into the second fastest LUT pin. Synthesis, placement, and packing tools can advantage of cascade connectivity to a great fast and efficient macros implemented within the LUTs and the cascade path. An additional output named PROP in figure 5b, PROP is added to implement carrier head functionality, which we describe in section 3.1.3. So next is 3.1.2 wide function. We chose to remove two dedicated wide function muxes that existed in the ultra scale in favor of the targeting more versatile LUTs for this function. Although the dedicated wide function muxes enable fast, efficient and compact implementations, and they lack placement or routing flexibility for designers with many wide functions. So a synthesis tool has two options. It could use dedicated wide function logic in the CLB and synthesizes the same logic using the regular LUTs. Wide functions implemented using dedicated logic result in a large object which have far more pins than a typical LUT. So hard 32-bit input mux will have around 37-bit inputs and 1 output. Placement algorithms do not perform well when they are asked to place instances with a widely varying pin count. As a result, it was observed that using the hardened wide function often features resulted in worse overall performance, worse wire length, and tougher to route designs. By implementing wide functions in LUTs, tools can build muxes that span multiple slices, to spread up mux out if necessary, and support a greater variety of topologies, priority muxes, and unbalanced or sparse trees, and etc. The global speed advantages of more flex architecture offset the local speed advantages of the prior hardened solution. The effect of this modification on the worst-case critical path of a suite of customer designs is shown in figure 6b. The normalized geomean of this suite of the designs does not change, with some outliers showing an increase in critical path of the 14%. We found that this is an acceptable trade-off for reduced area usage in all designs. Figure 6. The comparison between the ultra scale and Versal. Dual LUTs packing a soft and hard wide function mux. The 3.1.3 carry chains. A significant portion of ultra scale is dedicated carry logic is removed in Versal. and observed into the LUT using the new cascade path. Figure figure 7. Dedicated carry logic area as a result reduced by a factor of 5 while keeping long carry chain speeds constant, comparing both nanometer. Elimination of these dedicated carry signals also lead to a reduction of CLB output muxing cost, since LUT's output double as both generic 8 LUT function and the arithmetic function output. The figure 7 is here. The figure 7 is ultra-scale and Versal carry logic, a bit structure only to be shown as Gaide inputs and not shown in the carry mode. So the next is 3.1.4 other CLB changes. The Versal-based CLB has 25% fewer outputs per LUT compared to the ultra-scale CLB, and we converted data into the additional connectivity for each CLB output at a roughly cost parity and increased routability. Each register in the CLB can be individually bypassed without affecting the packing density. This also provides more output pin or the options for internal LUTs in the CLB to drive interconnect, which improve the routing flexibility. Half of the LUTs in each CLB are capable of functions as distributed memories or shift registers. Our analysis showed that a deeper LUT RAM mode 128 to 56 and 5 and 12 bits were used in the less than 1% of all instances. Hence, hardened support for these modes were removed in favor of a soft decoder based solution. In favor of a soft decoder based solution. The combination of these changes make for more streamlined and efficient CLB in the Versal architecture. Hard functions that were rarely used or whose use could be detrimental were removed and replaced by the enhanced LUT connectivities. The figure 7 ultra-scale Versal carry logic, as we already read. The next is section 3.2 local interconnect. 3.2.1 the CLB internal routing. A significant fraction of nets have very localized sources and destinations. An additional layer of routing muxes exists within a Versal-based CLB to achieve more success connecting local internal nets without requiring the general interconnect. Since local routes are shorter than can be squeezed with tighter pitches onto fewer lower level metal layers, and the implementation cost of local routes is substantially less than global routes. Thus, with the internal CLB routing structure in a Versal is almost every CLB out pins can drive every input pin on the same CLB using local route. We placed and routed the set of the customer designed on both the ultra-scale CLB and the Versal-based CLB, and report the number of the pin-to-pin connections contained within a single CLB. On average, we found that 18% of all pins to be 18% of all pin-to-pin connections are theoretically intra-CLB connections for the CLB inverter. Contrasted 7% within the smaller ultra-scale CLB. In figure 8a, this captures as a total internal connections. In practice, not all theoretical connections are achievable. However, we demonstrated that roughly 83% of those theoretical connections are actually routed in verse, compared to only about 28% of ultra-scale theoretical connections. Figure 8a illustrates this, as the internally satisfied connection shows only 2% of all nets in ultra-scale are successfully routed within a CLB compared to the 15% in Versa, increasing internal net routing by the factor of almost 8 times, while only modestly increasing the cost of the CLB. The figure A, benefits of the local interconnect enhanced. A, internal routing software, a structure in a coarse CLB. B is enhanced interface to hard macro blocks. 3.2.2, the interface enhancement for hard macro blocks. Similarly to the Versa-based CLB, the local interconnection structure was added to the interface of every hard macro, VRAM, DSP, PCIe, and etc., to enhance routability for highly utilized and congested designs. Every path from the general interconnect to a hard block goes through a layer of interconnect muxing structure within which reduces the stress of the general interconnect. To illustrate this, we experimented with simple designs consisting of a register driving the input pins of a hard macro block at various utilizations. We constrained the register to be some distance away horizontally and let the placer choose their destinations with the constraint region. We routed the design without interface enhancement and reported the normalized wire length of the figure 8b. We saw decreased wire length within the interface and count enhancement, and the wire length gap widened the higher bit utilizations, which indicate that the stress on global interconnect is reduced. So this is figure 9 is the Imux register. I think Imux register here. The 3.3 Imux registers. In order to facilitate the easier implementation of a high-performance design, we introduced a new feature to Fabric called the Imux Register Interface, IRI. Imux is the traditional name of the input muxing to each block. Imux registers placed in line with the Imuxes. These are flexible, bypassable registers on the input side of the all blocks. Compared to an approach where the registers exist in every interconnected resources, this registers everywhere approaching, the Imux registers are more cost-effective solution to increasing the design speed while requiring far less design adaptation. In the registers everywhere approaching, there is significant negative upfront performance tax. A sea of the interconnected registers increases the delay of every routing resource when not used in every route. Secondly, a cost mandate that resulting the register be a simple flop with no enable, reset, and initialization functionality. So adding control sets increase the cost of registers themselves. Plus the infrastructure necessary to connect control signals would be prohibitive. Thirdly, structural constraints such as the presence of sequential loops as pipeline balancing and hold requirement typing constrain how aggressively one can use pipeline. Registers on every MUX can simply not be used due to those constraints. With the IRI, the Versal architecture adds a substantial amount of registers, but not beyond what are usable. Each register is far more capable. Each register is fully features and supports clock enable, reset, and initialization, as well as time shifting capabilities. As with any added resource, the registers have a cost in terms of area and delay. However, as we demonstrate, even without any user design modification. So IRI delivers a performance increase, not decrease, for most designs. The Versal architecture supports aggressive time borrowing the techniques described in 18. We support time borrowing at a much finer level than in 18. The ultra scale plus enables time shifting only for a clock shared by 30 CLB slices, whereas the Versa has per CLB slice time shifting capabilities. The programmable delay lines per CLB can be used by itself or in a concert with a pipeline. Figure 9 shows the different cycle time reduction is both supported. Time borrowing enables the register to act as if it existed out in the interconnect. And still effectively bisect timing path. Figure 12 illustrates this effect and other modes and how each one reduces cycle time. Additionally, the ARI support of hold fishing mode. Each Imux register can be optionally clocked on the opposite clock edge, storing data from for a half a cycle. This time borrowing is often limited in practice by how many registers share the same delay. Borrowing time on a register may cause a hold violation for other registers within the same cluster. By selective using the hold fixing mode, thus more aggressive time to borrowing is available. So figure 10 demonstrates how hold fixing mode works by shifting data I away from the clock edge to avoid indeterminacy. The figure 10 hold fixing mode timing waveform. The figure 11 illustrates the average time impact of various modes across the suite of custom designs, limiting design modification to pipeline insertion, no redesign of the feedback loops. We use the same set of the customer design to also compare with our own registers and everywhere approach. Adding Imux register to our architecture incurs an initial penalty of about 4% due to a growth of block width, which stretches horizontal routing the resources, and additional delay of the A, growth of the block width. The B is the additional delay of bypassing the new register. However, the additional benefit to time borrowing more than offset the initial penalty. Note that these benefits do not require any design modification and has improved performance. Unlike our approach, our registers everywhere approach incurs a large initial penalty that cannot be recovered without a pipeline insertion of retiming. If one assuming that the design were indeed allowed to be pipelined, and a pipelining was the only technique applied, then the registers everywhere approach has better performance than the AI flops approach. However, when they use the pipelining in conjunction with the time borrowing simultaneously, a feature that for practical purposes can only exist in the IRI implementation, we are able to minimize the gap in the high end. In short, IRI register approach can deliver performance very close to that achieved by the registers, whereas approaching, but a fraction of the cost in area and power. Moreover, this approach also benefits traditional designs where design modification in form of adding a pipeline stage is not permitted. Figure 12, cycle time reduction from pipeline and time borrowing. Section 4 is SIT. What is SIT? First, Versal uses a 4th generation stacked silicon interposer technology, SSIT, to construct the ultra-scale and heterogeneous devices at a reasonable cost. Multiple active silicon dies called superlogic regions, SLRs, are stacked on a passive interposer and connected together, although the microdome bombs and metal traces on the interposer. Prior works to show that a total number of the SLR routing tracks, or SLRs, is about 25% of the routing tracks observed in an arbitrary horizontal cut within the SLR. Therefore, the place and route tools need to have awareness of the multi-SLR architecture and the inter-die interfaces, and the design may be partitioned with a minimal number of connections between SLR to reduce delays and routing congestion at the SLR boundaries. 4.1 as a SLL interface architecture, SLL channel architecture. A is routing based, B is tile based. We classified SLL interface architecture in the previous SSI based devices as routing based and logic based, logic tile based in 28 nanometer based 7 series Xilinx FPGAs. The interface were a routing based connection to the microphone from the FPGA fabric were made directly on the routing channels. Tri-stated wires on each individual SLR were shorted the interposer, which allowed to the routers to treat the SLR just as another routing resource with drivers and loads in different SLRs. Since the routing channels are ubiquitous on the FPGA fabric relative to the logic tiles, this had a software effect of the simplifying extending the existing routing infrastructure. The 20 or the 16 nanometer based ultra-scale FPGAs introduced the Laguna tile, which were specialized logic tiles that displaced the CLB tiles at each SLR boundary. Laguna tiles contain optional registers to create fast synchronous SLR connections across the SLR boundaries. This achieved inter-SLR frequencies of more than 500 MHz in the -2 speed degrade. However, to minimize the total Laguna cost, each column of Laguna tiles appears relatively infrequently compared routing-based approach and has much greater inter-SLR connections per channel. Show that in concentration of inter-SLR connections and Laguna, tile channels could result in a routability hotspot. So the first SSI architecture connecting the SLRs includes a hybrid approach that maximizes the benefit of the both routing-based and logic tiles-based SLL interfaces. Instead of a standalone Laguna tile, we distribute and embedded the SLR interface into each CLB. Costs are kept at a minimum by leveraging the CLB's interconnect and the internal routing. We take advantage of a larger 4 times CLB's internal routing structure as described in section 3 and to provide local access to each SLL. This internal routing structure also provides fast connectivity to and from registers within the CLB. As shown in the figure 14, the registers have optional bypass capability, which allows the SLR interface to operate synchronously or asynchronously. In addition, the same register type and intra-set granularities is used for intra-SLR and inter-SLR connections, giving more options on the placement of given registers. Similar to the routing-based SLR interface, there are significantly more SLL channels and fewer tracks per channel. The figure 15 is SLR interface, like this. Laguna tile interfaces distributes SLR interface. So now, the figure 16 is about is a horizontal estimated channel demand. The sample ultra-scale device contains 11 SLR channels, while the Versal contains 33. And the next is near the SLR edge. The pattern connects the SLBs in the one SLR to another toward the center of the SLR. The pattern creates a full mesh connection SLBs within the same SLR. We discussed the intra-SLR routing into the following section. In figure 16, we use the evaluation methodology described in 19 to the reference 19 to the implement multi-SLR synthetic design to control the inter-SLR connectivity. We compute the horizontal estimated channel demand and the number of the SLL channels per device increases while keeping the total number of the SLRs constant. We observe the decline in a horizontal track demand that will increase the number of the SLR channels as the SLR demand grows the incremental benefit of the adding of more SLR channels as the channels is greater. When 80% of SLRs are used, the horizontal congestion reduced by the 50% in the Versal or hybrid versus its ultra-scale and tile-based operation. The reduction in horizontal congestion directly translated to the better routability. So we also observed a 40% reduction in horizontal wire length and a 5% improvement in routability with the Versal hybrid SLR interfaces versus ultra-scale tile-based Laguna interface. So the 4.2 intra-SLR routing, as shown in figure 15, the Versal architecture also takes advantages of the interposer to create a full mesh of the long-distance wires both between and within the SLRs. This results in a more scalable routing architecture, since larger SSID devices, which typically are targeted for design of a higher routing complexity, have an extra layer of routing the smaller devices do not have to pay for. This feature do not exist in any prior SSID architectures. The long wires on the interposer are about 30% faster than a regular interconnect router for similar logical instances. So the long SSL wires on the interposer alleviated both horizontal and vertical routing and congestion by the freeing up a local routing resources. Across our suite of the design, we observed an 80% reduction in the horizontal wire length of the 6% reduction in the vertical wire length within the HSLR due to the interposer routing structure. The reduction is greater for designs that span a higher number of the SLRs. The next is section 5, global subsystems. 5.1, the global clocking. The FPGA architectures have the unique problem of supporting many clock networks in spatial variable locations. The metal resistance is not scaling well, so as the transistor delays continue to improve, clock delays associated with the long wires do not. The CPUs and ASICs often use thick metal layers to distribute clocks. FPGAs cannot afford this without sacrificing the clock capacity. So since clock load locations are not predefined, many clocks must run throughout a chip in a parallel. So in addition, FPGA architectures cannot afford to have a per device fully customized clocking solutions. The Versal architecture needed to scale in order to support several device variants that span an order of magnitude in size. At the same time, the clock frequencies continue to increase to keep up with the external bandwidth demand. Clock skew as a percentage of cycle overhead thus increases too. We used a three-pronged approach to reduce clocking overhead. 1. Adaptive clock deskew, and 2. Deskew. 2. Isolated clock supplies, and 3 is local clock dividers. And the figure 17 is skew as a fraction of clock period as a function of frequency. So even both two perfectly balanced clock tree incurs skew its penalties primarily due to the process mismatch along nominally matched path. In order to reduce clock skew without sacrificing clocking capacity, we implemented an adaptive clock skew scheme that actively modulated delays within the clock trees so that the process variation and even topological variation are turned out. The traditional skew is computed based on a min-max spread of the possible arrival times set by the range of the process can values for a given speed grade, which become untenable for higher speed and design. Adaptive deskew tunes propagation delays so that the process variation become a non-factor, increasing the Fmax of the old designs but specifically for higher performance ones. Figure 17 shows a suite of ultra-scale-based customer designs that illustrate the trend of higher frequency designs incurring greater clock skew penalties. The Versal devices are broken into a grid of fabric regions, where each fabric region denotes the clocking segmentation at each boundaries. The number of fabric The regions varies based on a device from the less than 10 to over 100. The Versal adaptive deskew scheme has phase detectors at each fabric region boundary. These phase detectors send the phase mismatch information back to the delay line and state the machine within each fabric region based on phase detector feedbacks. Each fabric region auto-negotiated its own delay until the phase mismatches at all adjacent boundaries are minimized. Figure 18b shows one the figure 18 impact of adaptive deskew. A is skew improved due to the adaptive deskew, and B is clock injected delays per region as adaptive deskew is enabled. So the 18 they showed one simulation result a relatively magnitude comparison where each line represents a delay to a given fabric region over time before and after the adaptive deskew is enabled. Each disk state machine is initially programmed by a software polynomial equalizes delay from the clock source to each fabric region. Then the adaptive deskew system is enabled to match actual silicon delays at the fabric region boundaries. To make the process transparent to the user, the entire skew process occurs as a step during the configuration using a compilation clock, so that the user clocks need not be active and continuously running. So the adaptive deskew directly minimizes the region to region clock skew, but in turn also reduces global skew. The same scheme is also used across SSID boundaries, so that the historically higher clock skew between SLR is also critically reduced. We expect to enable registering of the inter-die paths on both source and destination sides in a system-synchronous environment without causing a holding violations and speeding the special software support. As shown in the figure 18a, the global clock skew are measured in terms of setup and holding intra or inter-die are all expected to reduce by 60% or more. In order to reduce clock jitter, the fabric region in the region clock spins are implemented in a more isolated supply, where the decoupling capacitors could be added more liberally. Although the client data jitters are largely uncorrelated over long distances, we found at the logical level data and the clock jitter are more correlated and thus kept the leaf level clocks on the local common supply. The timing closure between the related clocks generated from the same source can be challenging, since in most architectures the nearest common node from a timing perspective is at the PLL or the DLL, which can be a nanosecond away from the clock load. Designs that operate different portions of the same logical design and frequencies which are divided from master frequencies is now very common. We added a clock divider to every clock leaf, which allows a single clock to be distributed through the clock network, and then multiple frequencies generated locally at the leaf level. Interclock skew reduces the region by an order of magnitude, assuming the related clock is a divided version, divided for 2, 4, or 8 of the base clock. This not only improves the clock skew for paths with related clock frequencies, but it also results in a reduced global clock track demand. So in previous architectures, every variant of the master clock had to be routed in parallel across the entire device. So in Versal architecture, in the Versal architecture, we route only single master clock and derive divided frequencies as demanded by the placement. To reduce clocking power, we enable designers to use dual edge clocking in a way that is transparent to the user. Each clock belief can opportunistically use its clock divider to ascend the clock at the half rate, and then each fabric clock multiplies the clock back to its original frequency. Dual edge clocking introduced due to the cycle distortion, timing, penalty overhead, so software would enable only the clock leaves that may have sufficient select to the usually edge, since leaf clocks are further along the clock tree than a clock spins. There are many more of them than they consume the bulk of global clock power, roughly 80%, even though the clock spins send the clock at the full rate, and not all clock leaves use dual edge. Total clock power can still reduce substantially. For example, if the 80% of the clock leaves cannot take advantage of this feature, global clock power reduces by the 40%. The 5.2 network on a chip. FPGAs have been very successful in providing users with a bit level configurable interconnect. This interconnect emulates routing done during the design of a ASIC in the configurable fabric of an FPGA. The semantics that each routing resources present to a user are very similar, and the routing of a track in the ASIC design. Such a model provides tremendous flexibility in the way the users can map their design. But this fine level of granularity suffers from significant loss of efficiency. Secondly, the increase in the large portion of the device resources are now being spent in managing this communication. As was described in section 1, this problem is worsened by the interconnect technology trend as well. To address the issue of the bit level management, it makes sense to organize data movement into a wide standardized bus interfaces. ASIC and the SoCs faced similar problems as moving the many high bandwidth data stream. These were initially addressed by buses. A next step was increased bus pipelining. This was followed by a move to the point-to-point interconnect with many independent parallel paths. In addition to these was to fully packetize the data and control information to more efficiently use the wires and buffers in the network. These networks are now commonly referred to as NOC. In packed switch NOCs, the central physical resources are used to route communication between the multiple ports, thus increasing area efficiency. So therefore, FPGA researchers have similarly proposed various techniques to improve the efficiency of bit level interconnect. These include requiring users to reason at the word level rather than bit level. And to implement NOCs as hardened interconnect resources on the FPGA and the Versal architecture, we implement a hardened NOC as a separate level of interconnect, augmenting the traditional FPGA interconnect. The traditional FPGA interconnect continues to provide a bit level flexibility, but as more and more of the system level communication occurs in a structured fashion, the NOC is able to absorb much more of the interconnected demand. This separates system level communication implementation from computer implementation and traditional FPGA implementations, since both communication and compute were implemented in a programmable fabric designed with demanding the interconnect resulted in a reduced compute and vice versa. Moreover, it's now not as important to so-called located where the computer occurs with where communication needs of the computer are satisfied. Consider the concrete case of computer IP requiring access to some memory controller. In order to close the timing at a higher frequencies required to support high bandwidth, the computer would have to be placed close to the memory controller. Alternately, the physical implementation tools would have to be smart enough to insert on-demand pipelining. On the other hand, with the NOC, it's possible for a compute to be implemented anywhere in the FPGA. All it needs to do is hook up the nearest NOC port of the communication to occur at a guaranteed bandwidth. The figure 19 shows the topology of NOC in relation to the rest of device resources. The NOC topology is a compromise comprised between the increased routing flexibility and minimal perturbation to the rest of the fabric. Most academic NOC topologies focus on implementing a mesh. There are several advantages of a mesh topology in terms of routing flexibility. However, a pure mesh topology is expensive. It would be underutilized. In a verse, NOCs appear in the main fabric as columns. In a columnar architecture. The NOC column integrated with the rest of fabric just like any other block, DSP, MPRAM, and etc. would. Each column is sized sufficiently to be able to saturate the bandwidth of the DDR4 and LPDDR4 memory controller operating at the maximum supported speed. At the bottom and top of the device, there are a greater number of NOC channels that are interfaced with the processor and the memory controllers. The reason for higher bandwidth topologies at the top and the bottom edges is to provide some flexibility to resources that demand memory bandwidth from the more than one controller. Topologies with a higher cross-sectional bandwidth at the top and the bottom make compute corner placement an easier problem than it otherwise would have been. The figure 19 NOC conceptual the diagram like this. And the figure 9 shows the blocks that make up our NOC topology. The primary block is for a ported switch and which routes the traffic from any of the 4 ports to any other port. Prefers such as masters, slaves, or memory controller form the endpoint in this topology. Masters perform either a read or a write request addressing any of the slaves' memory controller, which in turn fulfill this request. Fabric ports can serve both masters and slaves. The physical transport is managed by the routing tables within each switch, which tells how to route each packet. It is the task of the NOC software layer to ensure that bandwidth demands are met without deadlocked. The NOC supports standard NOC AXI4 memory mapped to streaming semantics and different classes of the quality of services. It also supports multiple virtual channels to alleviate the head of the line of blocking the traffic and aid the deadlock-free routing. With the device, NOC provides ports that permit communication from a processor to all prefers. There are also NOC ports at regular intervals in the fabric for software implementation of some compute to communicate either with each other or with the prefers. So the NOC integrated the entire memory address space of the device. Any master is attached anywhere in the device, whether via the fabric or a processor. The subsystem can address any other slave in the device, where it is a port on the NOC or whether it is a memory controller. This level of integration is extended to the SSI devices as well, so that all masters can address any slave in any die using a uniform address space. 5.3 is configuration. The configuration system in the Versal architecture has increased both in terms of capability as well as configuration speed. By pipelining the configuration infrastructure and increasing the config bus width, we were able to achieve an 8 times speedup in terms of configuration time per bit. Any design that configures frequently will have a less configuration overhead and more time for computation. Readback speeds are even more pronounced at 56 to 300 times relative to ultra-scale. This is due to a combination of configuration, infrastructure speedup, and concentrating float state readback memory into a fewer address frames. Read pipeline efficiency gains and enabling parallel readback of multiple dies in a device. For designs with a pure Fmax, 50 MHz or less, it is possible to take snapshots of the design state without stopping the clock. The platform management control, the PMC, is a dedicated processor that handles device management control functions such as power sequencing, initialization, boot configuration, security, power management, and health monitoring. It consists of a hardened micro-bridge core, boot ROM, as preferred interfaces, security accelerators, and power management units. Similar to ultra-scale devices, fabric blocks are configured via a distributed array of memory cells controlled by a grid of address and data lines, relying on the same system to program the preferred blocks, however, is problematic. Similar, primarily because these blocks have no fixed physical relationship with the interior fabric. So an additional configuration mechanism was added to the service. This block that runs in a tandem with the NOC, known as the NOC Preferred Interface, NIP. NPI. NPI is a streamlined packet-based switch network that allows in a tree structure to the preferred blocks and is seamlessly integrated with the configuration sequencing. The PMC can selectively write to and pull state registers on a specific endpoints. Write to and pull. From a partial reconfiguration standpoint, reconfigurable region granularity has become finer. The most configuration regions are now the size of a single block, and the blocks that share common feature space are separated logically to minimize loss in a functionality when requiring specific regions to reconfigure. Next is just section 6, conclusion. Xilinx addresses current semiconductor technological, economical, and scalability challenges, and the new 7nm ACAP heterogeneous compute platform. The Versal architecture tightly integrated the programmable fabric, CPUs and software programmable acceleration engines into a single device that enables higher levels of the software abstraction, enabling more rapid development of the hardware accelerators that solve next generation problems. Okay, there's a reference. Today I read this white paper or just paper, the Xilinx's adaptive computer acceleration platform, ACAP, Versal architecture. Thank you for your time and see you next time.